Transmission lines form the critical backbone of modern power systems, serving as the specialized conductors that carry bulk electrical energy over long distances from generating stations to load centers. Operating at voltages ranging from 33 kV to as high as 1200 kV, these lines are designed to minimize resistive losses through a fundamental principle: raising the voltage by a factor of 10 reduces the current by the same factor, thereby cutting I2 or losses by a factor of 100 for the same power transfer. Transmission lines are broadly classified by voltage level from low tension below 1 kV through high tension, extra high voltage, and ultra high voltage categories by length, where short lines under 80 km can ignore shunt capacitance while long lines exceeding 250 km require distributed parameter models, and by current type, encompassing the dominant high voltage alternating current, HVAC, high voltage direct current, HVDC, and the emerging ultra high voltage DC, UHVDC, technologies. Approximately 95% of global transmission infrastructure relies on HVAC, with HVDC accounting for roughly 5% but growing rapidly, while UHVDC represents less than 1% but is emerging as a transformative technology for continental-scale power transfer. The behavior of any transmission line is governed by four fundamental parameters: resistance, inductance, capacitance, and conductance. Resistance depends on conductor material, cross-sectional area, and temperature, with the skin effect increasing effective resistance at higher frequencies. Inductance arises from magnetic flux linkage between conductors and is characterized by geometric mean distance and geometric mean radius, producing series reactance that causes voltage drop. Capacitance between conductors and ground becomes significant for medium and long lines, introducing charging current and the Ferranti effect where receiving end voltage can exceed sending end voltage under light load conditions. Conductance, representing leakage current through insulators, is usually negligible except under polluted conditions. These parameters combine into the concept of surge impedance loading, defined as SL equals V superscript 2 divided by ZC, where ZC is the square root of the ratio of inductance to capacitance. At surge impedance loading, reactive power flow is balanced with no net VARs, and for a typical 400 kV line this corresponds to approximately 400 to 600 megawatts. High-voltage alternating current transmission has dominated the global power landscape for over a century, leveraging the simplicity of transformers for voltage step-up and step-down, the robustness of induction motors, and a well-established ecosystem of standards, protection systems, and manufacturing expertise. Typical HVAC systems operate as three-phase networks at 50 or 60 Hz, with voltage levels progressing from 66 kV through 132 kV, 220 kV, 400 kV, and 765 kV, with the highest operational voltage reaching 1200 kV in China.